Hello everyone, welcome back to my YouTube channel. So for this week's video, I'm going to explain to you how you should answer Test 1 question Set B. Altogether, we have 8 different questions and let's start with the first one. Question number 1. An aqueous solution of zinc chloride was produced when 1.34 gram of zinc powder reacts with 60 ml of 0.75 molar aqueous solution of hydrochloric acid at 36 degrees Celsius. During the reaction, 3.14 kilojoule of heat is produced. Estimate the change in internal energy of the reaction in kilojoule if 1 mole of zinc chloride is produced in the reaction. The first step in answering this question is to write a balance equation for the reaction. This reaction consists of reaction between zinc and also hydrochloric acid, which shall eventually produce zinc chloride and also hydrogen gas. So what we need to do is we need to balance up this equation, so we need to put 2 around here. So this is the balance equation for the reaction. Next, since we are given the mass of zinc powder, we can calculate the number of mole for the zinc. So the number of mole is equivalent to mass over RMM. And the mass was given in the question, which is 1.34 gram, and the RMM for zinc powder is equivalent to 65.38. Therefore, you will get 2.0496 times 10 to the power of negative 2 mole of zinc. Right? This is how much zinc is being used in the reaction. Next up, we are going to find what is the molarity. So given here, the molarity is 0.75. So molarity is equivalent to mole over liter. Given to you, the molarity is equivalent to 0.75. Therefore, we can find the number of moles. So the number of mole divided by the value for the volume is 60 milliliter, but we want it to be in liter, so we need to divide with 1000. Therefore, you will get the number of mole of the aqueous solution of hydrochloric acid is equivalent to 4.5 times 10 to the power of negative 2 mole of hydrochloric acid. Alright, so from the previous calculation, we have the number of mole for zinc and also hydrochloric acid. So from this information, what we can do is we can determine which one of this is the limiting reagent. So basically, 1 mole of zinc shall need 2 moles of HCl. What we are going to do is we are going to use the value of the number of mole for zinc. So we have 2.0496 times 10 to the power of negative 2 mole of zinc. Supposedly it needed 2 times 2.0496 times 10 to the power of negative 2. Therefore, we should get 4.0992 times 10 to the power of negative 2 mole of HCl. So this is how much HCl is needed for the reaction between this much zinc. Alright, but if we compare this value with the value of hydrochloric acid that is available, this is 4.5 times 10 to the power of negative 2, whereas we only need 4.0992 times 10 to the power of negative 2. Therefore, we can conclude that the zinc is actually the limiting reagent. So whatever heat is being produced shall reflect the amount of zinc available. Alright, next up what we are going to do is we are going to convert the heat from kilojoule to joule. Right, so in order to do that, you need to convert this kilojoule. So 3.14 kilojoule, you need to convert to joule. So you need to times 1000. So 3.14 times 1000, you shall get 3.14 times 10 to the power of 3 joule. Why do we need to convert this to joule? Although you were asked to calculate in kilojoule, because when you want to calculate the delta U, you will need to use the constant, the gas constant R, which is in joule. So we need to convert this first. And next up, what we are going to do is we are going to calculate what is your delta N. So what is your delta N? We need to refer back to our balance equation. So the equation is zinc in solid form will react with hydrochloric acid, definitely in aqueous form, and this will produce zinc chloride. So zinc chloride is actually in aqueous form and it shall produce hydrogen gas as well. So when we want to calculate the delta N, we only look at the state of matter of gas. So your delta N is equivalent to 1. So now what we are going to do is we are going to plug in all the values that we have and put it in the correct formula, which is delta U is equivalent to delta H minus RT delta N. So we are going to just plug in the values, the suitable values inside this formula. Alright, so before we can do that, we need to see what is the value of your delta H. Alright, so from the previous calculation, we know that our limiting reagent is zinc and the number of mole for zinc is this much. So in the question, it states that 3.14 kilojoule of heat is produced, but you were asked to calculate for just 1 mole of zinc chloride. So the concept that you need to understand here is your limiting reagent will dominate how much zinc chloride that will be produced. So in here we can say that 1 mole of zinc shall produce 1 mole of zinc chloride. Right? So the production of 1 mole of zinc chloride, so same goes here, because at the moment you have 2.0496 times 10 to the power of negative 2 mole of zinc. Therefore, it shall produce the same number of zinc chloride. So 2.0496 times 10 to the power of negative 2 zinc chloride is being produced. Why is this so important? Because this much of zinc chloride is being produced, and the heat that is produced in order for us to produce this zinc chloride is equivalent to 3.14 kilojoule. So what we can do here is for 2.0496 times 10 to the power of negative 2 mole of zinc chloride, it shall produce 3.14 times 10 to the power of 3 joule of heat. But in the question, you were asked to calculate for just 1 mole of zinc chloride. So it means that 3.14 times 10 to the power of 3 divided by 2.0496 times 10 to the power of negative 2. So you should get 1.5320 times 10 to the power of 5 joule of heat for 1 mole of zinc chloride. Okay, next up we are going to use the formula, but before that we are going to check whether our unit is correct. So in the question, it states here that heat is produced. So since heat is produced, it means that heat is being released. So when heat is being released, your delta H should be negative. Okay, next up we are going to look into the temperature. So here in the R constant, the temperature should be in Kelvin. So this one you need to plus 273, and we already calculated our N. So what we have to do next is we just need to plug in the values. So delta U is the thing we want to calculate. So delta H, because it should be negative, so we put negative here, negative 1.5320 times 10 to the power of 5 joule minus R. Your R is 8.3145 and your T is equivalent to 36 plus 273, and your delta N is equivalent to 1. So what we are going to do is we're just going to copy back 1.5320 times 10 to the power of 5 joule minus 8.3145, and the temperature is 309 times 1. Therefore, you will get your delta U equivalent to negative 1.5577 times 10 to the power of 5 joule. Alright, we need to check again. In the question, you were asked to calculate in kilojoules. So now we are going to convert again the unit from joule to kilojoule. So negative 1.5577 times 10 to the power of 5 divided by 1000. Therefore, you will get your delta U equivalent to negative 1.5577 times 10 to the power of 2 kilojoule. So this is the final answer for the first question. Alright guys, let's move on to question number 2. A piece of metal weighing 5.9047 times 10 to the power of negative 2 kilogram was heated to 100 degrees Celsius and then put into 100 ml of water initially at 296.7 Kelvin. The metal and water were allowed to come to an equilibrium temperature determined to be 300.8 Kelvin. Assuming no heat lost to the environment, calculate the specific heat of the metal given that the specific heat of water is equivalent to 4.184 joule per gram per degree Celsius. So relating to the first law of thermodynamics, heat cannot be destroyed or being created. Therefore, we can consider as the Q for metal plus the Q for water is equivalent to 0, whereby the Q is equivalent to ms delta T. Next up, we need to check the unit given to you. The specific heat of water is in joule per gram per degree Celsius, but the metal is in kilogram. And here it states here that the water is also in milliliter. So for the water, because of the density, we know that 100 milliliter of water is equivalent to 100 grams. So what we need to do now is we need to convert 5.9047 times 10 to the power of negative 2 kilogram into gram. So kilogram into gram, so times 1000. So this one you need to times 1000. So at the end you will get 59.047 grams for the piece of metal. Alright, now what we are going to do is we're just going to plug in this value. So since we already know the mass of the metal in grams, so we are just going to plug it in. So 59.047 gram of metal. So we have the specific heat that we need to calculate ms delta T. So your delta T, what is the delta T? The final temperature given in the question is 300.8 Kelvin, and the initial temperature of the metal is 100 degrees Celsius. So 100 plus 273. Right, we are settled with the metal. So we need to plus the information for the water. 100 milliliter of water is 100 gram. And then the specific heat is given in the question, 4.184. And the delta T, so the final temperature is the same, 300.8 Kelvin minus the initial temperature. So the initial temperature of water is 296.7. Therefore, we can get, I'm just going to write this again. So 59.047 gram, and then the specific heat, and here should be negative 72.2 Kelvin. And the other side is 100, and the specific heat given in the question is 4.184, and the temperature, the delta T, is equivalent to 4.1. So this value is actually equivalent to 0. Therefore, you just need to press your calculator. You should get your S is equivalent to 1715.44 divided by 4263.1934, and therefore you will get your S is equivalent to 0.4023 joule per gram per degree Celsius. So this is the final answer for the second question. Alright, let's move on to question number 3. A total of 0.2436 gram of an unknown substance was dissolved in 20 ml of cyclohexane. Given that the density and the freezing point depression of cyclohexane are 0.779 gram per ml and 20.2 degrees Celsius per molar respectively. By using your knowledge in the colligative properties of solution, determine the molar mass of the unknown substance if the delta T freezing is equivalent to 2.50 degrees Celsius. So first up, what we are going to do is we are going to find the mass of the cyclohexane, because given to you is the density of the cyclohexane. So the mass of cyclohexane is equivalent to the density, which is 0.779 gram per ml, times the volume of the cyclohexane given in the question, which is 20 ml. So therefore, the mass of the cyclohexane should be equivalent to 1.5580 times 10 to the power of 1 gram. So this is the mass of your cyclohexane. But since we are going to find the molality, because you have this, the freezing point depression should have the molality. So you need this cyclohexane, which is the solvent, to be in kilogram. So from gram, we need to convert to kilograms. So kilogram to gram times 1000. So we need to reverse back. Gram to kilogram, you need to divide by 1000. So we will get the conversion to kilogram is equivalent to 1.5580 times 10 to the power of negative 2 kilogram of cyclohexane. So this is the first step that you need to do. So next, we can use this information whereby we know that the delta T is equivalent to 2.50 degrees Celsius. So delta T freezing is equivalent to Kf, the freezing point depression, molality, and also the Van Hoff factor. So what is your Van Hoff factor? So I is equivalent to what? So this is a cyclohexane which shall not dissociate completely. So your I or your Van Hoff factor should be equivalent to 1. And then you already know the delta T freezing is equivalent to 2.50, and your Kf freezing point depression is equivalent to 20.2 degrees Celsius per molar. So here 20.2. So you need to find your molality. So molality, what is your molality? So molality is mole of solute divided by the mass of solvent, but the mass must be in kilogram. So then you need to times your Van Hoff factor, which is equivalent to 1. So this one we already calculated just now, so we just need to plug in that value. So this one Tf is equivalent to 0.25, just like in the question. Kf is given in the question as well. So mole of solute divided by the mass of solvent, just now we have already calculated 1.5580 times 10 to the power of negative 2 kilogram, and your I is equivalent to 1. Therefore, you will get your mole of solute should be equivalent to 2.5 times 1.5580 times 10 to the power of negative 2 divided by 20.2. Therefore, you will get 1.9282 times 10 to the power of negative 3. So this is the mole of solute. So from there, you can find, because you already know what is the number of moles, so we can find what is the molar mass of the unknown substance, because you already know the mole of solute. So number of mole is equivalent to mass over RMM. Alright, so we already know the mass and we already know what is the number of mole. Definitely we can find the RMM. Alright, let's calculate the RMM together. So the number of mole is equivalent to mass over RMM. So the number of mole is the thing that we calculated just now, which is 1.9282 times 10 to the power of negative 3. And the mass is given to you in the question, 0.2436 gram over RMM. Therefore, your RMM should be equivalent to 0.2436 divided by 1.9282 times 10 to the power of negative 3. Therefore, your RMM should be equivalent to 1.2634 times 10 to the power of 2. So this is the final answer for this question. Question number 4. Calculate the concentration of an aqueous solution of trisodium phosphate if its ionic strength is equivalent to 0.06 molar. Right, so the concentration of aqueous solution of trisodium phosphate is asked from you when it gives you the ionic strength. So the trisodium phosphate, so from here you need to make it into its ionic form. So you know your sodium is an A+. So since you need 3 of this, so you know your phosphate is actually 3 negative. So from there you can use the ionic strength formula is equivalent to 1 over 2 the summation of the concentration and the charge to the power of 2. Given to you in the question is the ionic strength. So ionic strength is equivalent to 0.06 is equivalent to 1 over 2 and then the first one we are going to do is 3x, because we have 3 sodium here. We put x because we don't know the concentration, times positive 1 to the power of 2 plus, we also don't know the concentration, right, because it's the only solution here. So the other one is just 1 phosphate, so x times the phosphate is negative 3 to the power of 2. So from here we will get 0.06 is equivalent to half times 3x plus 9x. So 3 plus 9 is equivalent to 12x. So 6x. Therefore, 6x is equivalent to 0.06. So your x is 0.06 divided by 6. Your x is equivalent to 0.01. So this is the final answer, whereby your concentration is equivalent to 0.01 molar. Question number 5. Nitrogen dioxide dissociate to produce oxygen gas and gas X. If the dissociation reaction was conducted at 98 degrees Celsius, determine the partial pressure of gas X if the partial pressure of oxygen and the Kc of the reaction is equivalent to 0.25 atm and 5.1873 respectively. Alright, so this is a rather direct question. So the first thing that you need to do is you need to write the dissociation of nitrogen dioxide. So basically your nitrogen dioxide will dissociate into nitrogen monoxide and also oxygen gas. So all of these are in gaseous form. And the next thing that you need to do is you need to balance out this equation. So basically around here you have 3 oxygen, so here you only have 2. So the best way is to put 2 around here so that you can get 4. So you need to put here 2 as well. So you have 2 nitrogen in the reactant and 2 in the product as well. So this is the balance equation for the dissociation of nitrogen dioxide. So again, in the question it stated that you are going to produce gas X. So 1 is oxygen, therefore your gas X is nitrogen monoxide. So what are you going to do next is we are going to write the ice diagram for this dissociation process. Alright, so from the question we know that we have no value for the initial concentration or initial pressure for nitrogen dioxide. So what we are going to do is we're just going to put Y around here. At the beginning there's no dissociation occurring, so it's 0 and 0. So at change you will have negative 2x and here positive 2x. Here is going to be x. Therefore at equilibrium is going to be y minus 2x. Here will be 2x and x. Alright, if you look at the question, it states here that the partial pressure of oxygen is equivalent to 0.25 atm. So the only place that we can find the oxygen is at equilibrium. Therefore we can say that your x is equivalent to 0.25. So what we can do is we need to substitute all the x's with 0.25. So here is 0.25. Here is going to be 2 times 0.25, where this one y minus 2 times 0.25. Alright, but if you check back on your questions, you were asked to determine the partial pressure of gas X. So the partial pressure for gas X is this one. So what we are going to do is just the partial pressure of gas X NO2 is equivalent to 2 times 0.25. Therefore, we will get 0.5 atm. So this is the final answer for the fifth question. Moving on to question number 6. 2.5 liter container at 0 degrees Celsius contains 0.06 mole of hydrogen gas, 0.0024 mole of oxygen gas, and 0.0002 mole of methane. Assuming these gases behaves as an ideal gases, predict the partial pressure of the oxygen gas. Alright, to answer this question, the first thing that you need to do is you need to calculate the mole fraction of oxygen gas. So the mole fraction of oxygen gas is equivalent to the number of mole of oxygen gas divided by total number of mole. So from the question, we know that the number of mole of oxygen gas is equivalent to 0.0024 mole, and then the total number of mole is 0.006 plus 0.0024 and 0.0002. Therefore, we will get 0.0024 divided by 8.6 times 10 to the power of negative 3. Therefore, you will get the mole fraction of oxygen gas is equivalent to 2.7907 times 10 to the power of negative 1. Alright, so the next up is you need to know what is the total pressure. So how are you going to get the total pressure? Because it states here that it behaves as an ideal gases. So you can use the ideal gas law. So PV equivalent to nRT. Therefore, you will get the pressure, which is the total pressure. Alright, so let's calculate the total pressure together. So we are going to use PV equivalent to nRT. So P is the one that we are going to calculate, and your V is 2.5 because the container is 2.5 liter. Your N is actually the total number of mole, which is 8.6 times 10 to the power of negative 3. R is the gas constant, 0.0821, and your T is 0 degrees Celsius. Since your R is in Kelvin, so 0 plus 273. Therefore, you will get your P is actually equivalent to 1.9275 times 10 to the power of negative 1 divided by 2.5. Therefore, you will get your P, which is the total pressure, is equivalent to 7.7100 times 10 to the power of negative 2 atm. So this is the total pressure. And you were asked to predict the partial pressure of oxygen gas. So the partial pressure of oxygen gas is equivalent to the mole fraction times the total pressure. So the mole fraction is being calculated just now. So the mole fraction that you got for oxygen gas is 2.7907 times 10 to the power of negative 1. And your total pressure is the one we have just calculated. So you need to times 7.7100 times 10 to the power of negative 2. Therefore, the partial pressure for oxygen gas is 2.1516 times 10 to the power of negative 2 atm. So this is the final answer for the sixth question. Moving on to question number 6. The reaction below was conducted at 88 degrees Celsius. At the beginning of the reaction, 0.3 mole of nitrogen monoxide, 0.2 mole of chlorine, and 0.5 mole of nitrosyl chloride were placed in a 25-liter container. At equilibrium, 0.6 mole of nitrosyl chloride are present. Determine the Kp of the reaction. This is a rather an easy question because you were given the balance equation for the reaction. So what we are going to do is we are going to use this equation and write it as the ice diagram. So from the question, it states here that at the beginning, so you have this much of substance. So we are just going to put it. So here is 0.5, and then you have 0.3 nitrogen monoxide and also 0.2 mole of chlorine. So a change is going to be negative 2x, and here positive 2x, here will be x. So at equilibrium is 0.5 minus 2x, 0.3 plus 2x, and here is equivalent to x. Right, and then it states here that at equilibrium, the nitrosyl chloride is 0.6 mole, means that over here is equivalent to 0.6 mole. So what we are going to do now is we are going to use this information to find what is the value of x. So 0.5 minus 2x is equivalent to 0.6. Therefore, minus 2x is equivalent to 0.6 minus 0.5. And your minus 2x is equivalent to 0.1. Hence, your x is equivalent to minus 0.1 divided by 2, which is minus 5 times 10 to the power of negative 2. So you already get the value of x. Alright, so now what we can do is we need to substitute all the x's with this value. So 0.5 minus 2 times negative 5 times 10 to the power of negative 2. And here is 0.3 plus 2 times negative 5 times 10 to the power of negative 2. And the last one is just negative 5 times 10 to the power of negative 2. So now you need to do is just to press your calculator. So you will get 0.6 mole. Here is 0.2 mole, and the last one is 0.15 mole. Now we need to check again the question, and in the question we were given the volume of the container. From this volume, you can convert the number of mole into the molarity. Right, so since we already know all the number of mole and we know the volume of the container, we can get the molarity. So molarity is the number of mole divided by the volume in liters. So given to you is already in liter, so 25. Here is going to be 0.2 divided by 25, and here is 0.15 divided by 25. Therefore, we shall get the molarity at equilibrium equivalent to 2.4 times 10 to the power of negative 2. This one will be 8.0 times 10 to the power of negative 3. And the last one will be 6.0 times 10 to the power of negative 3. So from this value, what we can do is we can calculate the Kc of the reaction. So Kc is equivalent to whatever in the product divided by whatever in the reactant. So Kc, we are going to look into the concentration, therefore we'll write it in a box bracket. So Cl2, and then we have NO to the power of 2 because we have 2 around here, divided by the concentration of ClNO to the power of 2 as well. Right now, so we are going to just substitute all this value inside the Kc. So Kc is equivalent to 6.0 times 10 to the power of negative 3 times 8.0 times 10 to the power of negative 3 to the power of 2 divided by 2.4 times 10 to the power of negative 2 also to the power of 2. So you will get your Kc equivalent to 6.6667 times 10 to the power of negative 4. But if you check again, you were asked to calculate the Kp, not the Kc. So the next thing that we need to do is we need to determine what is your delta N. So the delta N here, we are just going to refer to this equation. So we have 1 here and another 2 here and 2 over here. So product minus reactant. So your product is 2 plus 1 and your reactant is 2. So 3 minus 2, therefore your delta N is equivalent to 1. So delta N is equivalent to 3 minus 2 equivalent to 1. So from there, we can use the formula for Kp, which is Kp equivalent to Kc RT to the power of delta N. So you get your delta N already. Your R is a gas constant. The temperature is given to you in the question, which is 88 degrees Celsius. You already calculated your Kc just now. So definitely you can get the value for your Kp. Alright, so let's calculate the Kp together. So Kp is equivalent to Kc RT to the power of delta N. So your Kc from the calculation is 6.6667 times 10 to the power of negative 4. And then your R is the constant value, which is 0.0821, and your temperature is 88 degrees Celsius. So you need to convert this to Kelvin plus 273. And then from the calculation, we get your delta N is equivalent to 1. So this one shall be equivalent to 6.6667 times 10 to the power of negative 4 times 2.9638 times 10 to the power of 1. Therefore, you will get your Kp is 1.9759 times 10 to the power of negative 2. So this is the final answer for question number 7. Alright, now we are at the 8th question, which is the final question for this week's discussion video. So this is actually the continuation from the previous questions, and the question asked you to predict if the reaction is actually a product favored or a reactant favored. Alright, so in order for you to predict whether it is a product favored or a reactant favored reaction, you need to calculate your QC. So in order for you to calculate your QC, you need to calculate what is the initial concentration. So given in the question at the beginning of the reaction, these are the variables. So we're just going to plug in this value. So here is going to be 0.5. And the nitrogen monoxide is 0.3, and the last one is 0.2. The container is 25 liters, so we are going to find the molarity. So the molarity is equivalent to 0.5 divided by 25. Here is 0.3 divided by 25, and lastly 0.2 divided by 25. Therefore, after you have pressed your calculator, you should get the molarity as follows. This one is 2.0 times 10 to the power of negative 2. This one is 1.2 times 10 to the power of negative 2. And lastly is 8.0 times 10 to the power of negative 3. So from this value, what you are going to do is you are going to calculate your QC. So your QC is actually whatever in the product. So you will have the concentration of chlorine times the concentration of nitrogen monoxide to the power of 2 divided by concentration of ClNO to the power of 2 as well. So now we're just going to do the QC. So your QC is equivalent to the concentration of chlorine times the concentration of nitrogen monoxide to the power of 2 divided by the concentration of ClNO to the power of 2 as well. So we're just going to copy up the concentration. We have 8.0 times 10 to the power of negative 3. And then here we have 1.2 times 10 to the power of negative 2 to the power of 2 divided by 2.0 times 10 to the power of negative 2 to the power of 2 as well. Therefore, you shall end up with 1.1520 times 10 to the power of negative 6 divided by 4.0 times 10 to the power of negative 4. Hence, your QC should be equivalent to 2.88 times 10 to the power of negative 3. Right, so up next what we are going to do is we are going to compare this value with the value of Kc that we already calculated in the previous question. So in the previous question, we get your Kc is equivalent to 6.6667 times 10 to the power of negative 4. Therefore, from here, we can say that your QC is actually bigger than your Kc. Therefore, when your QC is bigger than your Kc, it is a reactant-favored reaction. In other words, the reaction shall proceed in the direction of the reactant. It will proceed to the left. So this is the final answer for the final question. Alright, we have reached the end of this week's video. Thank you very much for watching till the end. I hope that this video shall help you to understand more on how you should answer all the questions from the test 1 set B. If you think that this video is helpful to you, please give it a thumbs up and I'll see you again next week. Take care, be safe and be good. Goodbye.